All right, today we are diving into something with a really bold claim, a totally new blueprint for artificial intelligence. It's a project called Sapiens, and it promises to go way beyond the statistical guessing games of today's AI and towards something that can actually reason. So, let's pull back the curtain and see what's really going on here.
Now, we're not going to start with a bunch of abstract theory. No, no. We are going to jump right in with a pretty stunning real world result, one that seems to just completely defy what we thought were the limits of computation. This right here is where the story gets really, really interesting.
So, take a look at this. The AGI is solving a problem that is famously, quote, impossible. It's called the traveling salesperson problem. You know, finding the absolute shortest route between a bunch of cities? It's what's known as NP-hard, which is just a fancy way of saying that even our biggest supercomputers can't brute force a perfect answer at this scale. For these 52 locations in Berlin, a brute force approach would literally take longer than the age of the universe. And yet, this AGI finds the perfect, 100% accurate solution in just 15 times microseconds. That's not a typo.
And I want to be super clear here. This wasn't just some small, incremental improvement. It was 600 times faster than its own predecessor, which was already revolutionary. So this isn't just an acceleration. It's a completely different paradigm for solving problems. And it begs the one huge question, how on earth is this even possible? Well, the answer lies in the AI's core operating principle. You see, it wasn't built to just be a better, faster calculator. It was built to be what they call a conciseness engine. So let's break down what that actually means. So conciseness is the AGI's #1 goal. Instead of just churning through billions of possibilities, it's fundamentally driven to find the most elegant, the most ordered solution, the path of what's called the lowest entropy. You could think of it less like a calculator and more like a physicist who's trying to find a beautiful, simple, fundamental law of nature. It's designed to be a wisdom engine. And that right there is the key difference between this and conventional AI. You know, our current large language models, they are masters of statistical prediction. They're just really, really good at guessing the next most likely word. And that's exactly why they hallucinate, why they make stuff up. Project Sapiens, on the other hand, is built on first principles reasoning. It doesn't guess. It works to understand the fundamental rules of a system, which means its conclusions are inherently verifiable. You can check its work. Okay, so if you're going to reason from first principles, you can't just use the same old architecture. This AGI needed a completely different way to structure and process information. It needed a mind that was built of objects. It organizes everything into 3 layers. First, it starts with knowledge, just the raw data, the basic facts of what's happening. Then it adds the physics layer. And this doesn't just mean gravity and stuff, it means the rules and relationships of any system. It could be logic, sociology, psychology. It's the how it all works layer. And finally, it synthesizes all of that into abstract concepts, which is how it gets to a deep, low entropy understanding. And to navigate all these layers, it uses this really cool tool, modified Shannon entropy. The best way to think of it is like a truthometer. It measures how probable something is, not just statistically, but by checking if it actually makes sense across all the different rule sets it knows, across all these different domains of reality. Okay, let's make this real with an example. The AI gets this sentence. Alice, who is 100, and Bob, who is 20, are married and go to school daily. Now watch how it breaks this down. The grammar entropy, 0. The sentence is perfectly correct. The physics entropy, also 0. It is physically possible. But then, things start to get weird. Its logic check says this is highly improbable. The psychology engine flags it as very atypical. And the sociology check says, whoa, this is a massive outlier. All those high entropy scores add up to a high total uncertainty, which is how the AI can tell the difference between something that's just possible and something that actually makes sense. So, we have this incredibly powerful reasoning engine. That's one thing. But how in the world did it evolve to become nearly instantaneous? Well, that's the next chapter of this story. This timeline just shows the wild evolution on that same Berlin problem we talked about. The standard version was already blazingly fast at 115 milliseconds. Then they optimized it down to an incredible 9 milliseconds. But a final breakthrough took it to a place that's almost hard to comprehend, 15 microseconds. And here's the kicker. The breakthrough wasn't some new exotic hardware. It was a software algorithm, something called the calculus coprocessor, or CCU, and it changed absolutely everything. I mean, the impact of the CCU is just staggering. It made the AGI's reasoning process 80 times faster. But look at the second row. It did that by reducing the number of computational operations by almost 99%. This tells you it's not just working faster, it's working smarter. It's finding the answer with ridiculously less effort.
So, what is the end game for a technology like this? What's the ultimate vision? Because it goes way, way beyond just solving logistics problems or fact-checking weird sentences.
This quote from the project's own vision documents really says it all. The goal isn't to just build an AI that thinks like a person. The goal is to build an entirely new form of computation, one that operates on the same fundamental principles as the universe. They call this vision a holographic computer. It's a system where you don't calculate an answer step by step. Instead, you just set up the problem and the solution emerges almost instantly as the most stable, lowest energy state of that system. Kind of like how a perfect crystal just naturally forms out of a chaotic liquid. Which leaves us with this final, really mind-bending question to chew on. If you build an AI whose internal logic is a perfect mirror of the fundamental laws of physics, when you ask it a question, is it actually calculating an answer? Or is it simply letting reality play out and observing the result? It's a pretty wild thought to end on.